Thanks for the nice introduction. I am Xin He. You can call me Sean. I'm from City University, Hong Kong. I'm currently PhD student there. And this paper is co-authored with Will Cong from Cornell University, Guanghao Feng, and Jinyu He, both from City University, Hong Kong. This project is titled Asset Pricing with Penalties under Global Split Criteria. You can tell from the name, this paper is about asset pricing, and we propose a new tree-based model. It's called a panel tree with some other features. All right. So the motivation of this project is asset pricing factors. Common risk factors are used to describe the returns and average returns in finance literature and also the industry. For example, we have the market factor, which comes from the famous CAPM model. The market factor is simply the value-weighted portfolio of all the stocks or assets in the market. Also, we have the from a French type factors. They are the long-short portfolios based on some sorted portfolios. We have the size and a value. We can sort on that. After that, you get some basis portfolios. Then you do long-short on these basis portfolios. After that, you get small minus big or high minus low. That is from a French factors. Recently, we see some machine learning applications in finance. We have some machine learning factors like the PCA factors, different versions of PCA factors, deep learning factors, so on and so forth. But all of these machine learning methods, they both involve multiple firm characteristics like the size, value, momentum, and other features. So this paper, we use a panel tree model to generate a latent factor. And we have some interpretable nonlinear graphical representation you will see there. All right. So this paper, this machine learning is interpretable. It's white box instead of a black box model. All right. Our paper starts from the conditional, sorry, what's this? Okay, you're free to ask questions. So our paper is motivated from the conditional asset pricing model. You see this is the very general stochastic discount factor model in the textbook. So MT plus 1 is the stochastic discount factor, and IT plus 1 is the future excess return of the stock I. Okay, you can discount the future return back to now, and you see the expected return is 0. So this is the theory part. Okay, by some derivation, you have the right-hand side. The expected return of this stock in the next period equals the beta times the lambda. Beta is the factor exposure, and lambda is the risk premium of this factor. So notably, we have only one factor there. It is called the stochastic discount factor. Lambda t plus 1 is the risk premium for this one factor model. So how do we derive this factor? So in textbook, we say this thing. The MT is 1 minus W times the return vector. So we have to identify this W. So the W is like this. This is the covariance matrix inverse of all the stocks in the cross-section. And this is like the expected return of all the stocks in the cross-section. Now you find the difficulty to estimate this WT if you use the textbook example, because in a stock market, we have thousands of stocks. You have to estimate this covariance matrix, which has thousands times thousands dimension. So it is not feasible. So how do we solve this problem? We use basis portfolios. So the researchers divide all the stocks into some portfolios, and these portfolios are called basis portfolios. We generate the SDF based on these basis portfolios. So capital R is like the basis portfolio. For example, you have the industry portfolio. You can plug in and generate your version of the stochastic discount factor. Or you can use from a French 25 portfolios based on size and the value of the stocks. And you can plug in, get your factor. So once you have your capital R, you can generate the stochastic discount factor. And how about the betas? So in this paper, we use the time varying factor loading. So it is also called conditional beta. So in this framework, beta is quite complex. It looks like this in equation 6. But in our formula, in our algorithm, we simply use this reduced form approximation. So beta IT equals a linear form. It is a function of the sum stock characteristics. So JIT is like the size, value, momentum, reversal, these features of the stocks. All right. So you may notice the K there. So K is the tree depth. We'll see later. All right. So before I go to my model, I will introduce why we use decision tree. What is the advantage of tree models? But I guess in this forum, many of the audience is already very familiar with the tree models. So the famous tree model is CART by Breitman and the co-authors. Is a specific decision tree algorithm for classification or regression. One advantage is that researchers can split the cross-section and group the similar assets into portfolios by the past firm characteristics. So we have a very good economic interpretation there. It's like, so the tree model, it's like sorting in finance. The second advantage is tree model involves nonlinear structures, and you can plot the structure graphically. That is very interesting, and you know how the model looks like. But if you use a neural network, sometimes it will be criticized by black box. Okay, third, the tree model is highly adaptive to low signal to noise ratio data. So in finance, you know, the signal is very small, and most of the observations are noises. And in some machine learning application context like cargo, you can see random forest everywhere and boosted tree everywhere. So what are the disadvantages of the CART? First, CART assume the observations on IID. This is very strong assumption. Also, you can see this kind of assumption for many machine learning methods. But in this paper, our model consider the panel data structure in finance, and in many other economic research, you can see this kind of panel data structure. This is one disadvantage of CART. Second is the CART only involves recursive optimization, which means the tree grows layer by layer. For each leaf, you only consider the observations in this leaf, and you decide which point do you split the cross section. However, in our setup, we want a factor model that is useful for the whole cross section. You have to involve the whole cross section, the observations there, to make your decision. So in this paper, our model will use a global split criteria, and we are going to split the tree iteratively instead of recursively. All right, so let me remind you how tree works, and you will see how our model works. So for example, if we only have size and the value, these two features to model the stocks, we have this box there, and the points there are the stock month observations. Before the first split, you have only one portfolio. Okay, this is the market portfolio. After that, if you do some split in the cross section, for example, you split at 0.3 on size, you get two portfolios. Okay, so you're going to make decisions. Which variable do you split and which value do you split? You can split on size, you can split on value. And if you choose size, you can split on 0.1, 0.2, 0.3. So it all depends on your loss function. And what is the loss function for CART? It's like this. This is the L2 loss function. you can interpret it as pricing errors. So RIT is the stock return of stock I at time t. Upper left is the average of the observations on the left box. So this is the left box, and this is the right box. So for the left box, we use upper left as the model implied return for all the observations on the left, and we do the same thing for the right observations. So for card, it only works for ID assumptions, and but for finance, we have the imbalanced panel data for the stock returns. So we're going to see our panel tree model later. Also, as I told you before, card grows a tree recursively for local split criteria. We're going to look for common risk factors, and we're going to have a global criteria. All right, so this is our model, panel tree for asset pricing. And this is our loss function. So this is the stock return of stock I at time t, and this is the model implied return, mu IT at this tree structure K. So mu IT equals beta I times FT. This is the factor model framework, as you can see everywhere. So beta I is the risk exposure, FT is the factor. So our model will give you a factor, okay? And the FT superscript K is the factor generated after the case split of the tree. So previously we used the MT as the SDF, but now because many people in finance simply use FT, so now we use FT, but they are the same thing. Okay, now we have a factor, and what are the features of our panel tree? So our panel tree gives a multi-period model. Okay, it is a vector outcome instead of a scalar outcome. So for the card, we have this scalar outcome, but now we have the vector outcome, the FT. So it has to be the same tree for every period. And so every split has to consider all the observations in the cross-section for a common risk factor model. So we're going to split this tree iteratively. All right, questions so far? So panel tree factor model. Okay, next we're going to say how do we build this tree and step by step. Before any step, before any split, we start from R0. R0 is the market factor. Okay, it is the evaluated market factor for all the stocks. This RJ superscript K is the leaf basis portfolio of the J's terminal node after K's split. So for example, we split on this variable. It is the standard deviation of the trading volume at this number 0.2. We got two portfolios. We got two basic leaf basis portfolios, R11 and R21. Okay. R11 and R21 are the value-weighted portfolios for all the stocks in them. And the factor is essentially the mean variance efficient portfolio spanned by the leaf basis portfolios. You can simply imagine you have two basis portfolios, and now you have to calculate the tangent portfolio. Okay, that is the factor in our model. So in formula, you have something like this. Our tree will search for all the possible splits and calculate the loss function. Finally, the tree will find the best one that minimizes the loss function and do the split. So the loss function is like this, as we see before. The beta is modeled in reduced form. Okay, the betas are conditional on the past firm characteristics for individual stocks. And based on this loss function, what we do is essentially we run this panel regression. We regress the stock returns on the factors and also the interaction term of the characteristics and the factors. Okay. So simply we run this regression and say the goodness of fit of this regression. after all the searches, we make a decision which variable to split and which value to split. That is the first step right down here. Okay, for the second split, we can split on the left leaf or the right leaf. We can split on any variable and any value. Our tree algorithm will search among all the possible candidates. And after that, we have 3 basis portfolios, and you generate a new factor, you update the factor. All right. This is how we generate, how we update the trees iteratively, step by step. So finally, you will stop somewhere by some terminal condition, and you can restrict the tree grow low more than 4 depths. The portfolio contains at least 50 stocks there, so we don't want the portfolio to be too small. So you can set any terminal condition by yourself. All right. So this is how we grow our panel tree model. So this is for a single tree, okay, and we have 1 latent factor. But in practice, we have the multi-factor model. Okay, so our tree can also generate multi-factor model like this. We can use boosting scheme. We can combine boosting with our panel tree. So we already have the first tree and first factor. You can use the first factor to price all the stocks, and you get the residues. Okay, you get the residues. After that, you fit the residues with a second tree. Okay, this is your second factor. And similarly, you can do the third factor, fourth factor, and the fifth factor. You got a 3-factor model or 5-factor model. This is one extension. Okay, so you can start by our tree model as the first factor. Also, you can start from the market factor. Okay, you can use the market factor as the first factor, and then you use our tree to generate the second factor. So this is the so-called the market adjusted panel tree. You can see more details in your paper. I got a question. Okay, I got this question. So we have more extensions like the random forest to test the variable importance, blah, blah. You'll check more details in the paper. So we don't have more time. Let me go to the empirical findings. Also, I see the host asked this question: why do you normalize the characteristic in -1 one way? Why not Gaussian? And impact on the result of your model. All right. So our data is the recent 40 years data for the US stocks. We have the returns of the stocks and the lag 1 month characteristics. Okay, we use the past 1 month features to forecast the next period return. We standardize the characteristics in the cross-section into uniform distribution. And this is related to the question. So we standardize this characteristic simply for interpretation. You'll see later in the plot, you will see a less quantile number. But this standardization does not change the result. This standardization does not change the result at all, because in the tree model, when we split the cross-section, we always look at the quantile number instead of the absolute value. Okay, so you can standardize it or not. The result does not change. All right, we have 60 characteristics plus the size. So finally, we have 61. And we're going to show the empirical result with the first 20 year for training and the latest 20 year for testing. I know this is impractical for the industry person. You can adapt it to your model, and we just show this for academic purpose. All right. So this is the tree structure we have based on the previous 20-year data. We first split on the dollar trading volume standard deviation, and the second on the size, third on the momentum, blah, blah. Finally, we have 23 basis portfolios there, the leaves. All right. This is one way we can visualize this tree. You can see very clearly which variable is split, which value is split, and you can see the sequence of the splitting. And also we report this number. This is the median number of stocks in this portfolio for the 20 years. So we see these portfolios are big portfolios. We have at least 88 stocks in each portfolio. So we're not stopping at some very extreme cases. We got a question. How many stocks in each business portfolio here? I think I have answered the question. So this small number are the median number of stocks in this portfolio. And the minimum number of stocks in this portfolio is at least 50, I think. Yeah, these are tuning parameters. You can adapt it by your purpose. All right, let me show the second plot. This is a partition plot. This is exactly the same thing as you say in the tree plot. So first we split on trading volume. Second we split on the size. But this is a different way to visualize the tree. Okay. Also, we have some results for the random forest for the variable importance. We have different measures for variable importance based on different random forests. And the interesting part is here, the measure of asset price and performance. Okay, we have some R-squared there. So we're going to compare our model with some other factor models. So after rational, sorry. So we have the total R-squared and predicted R-squared, and also the cross-section R-squared to price the stocks. The total R-squared and the predicted R-squared are for individual stocks. So in panel A, we have our panel tree factors. In panel B, we have the market-adjusted version of the panel tree factors. And then in these others, we have the CAPM from French factors, recently published PCA factors. We find our 5-factor model is very strong compared to the existing factor models, and is persistently strong for auto sample. Okay. As for the portfolios, we find our market-adjusted panel tree portfolios. There are 18 portfolios, are very hard to be priced by the common risk factors. However, our model can price these 18 portfolios almost perfectly. So this is the contribution. So first, we find a very strong factor model. We can price these individual stocks and the portfolios. Second, we find a group of test assets that is very difficult to be priced by other factor models. All right. As for investment, again, maybe the audience are more interested because you come from the industry. Our one-factor model has an average monthly return of 1%, and the Sharpe ratio, the annualized Sharpe ratio is 0.66. And our 5-factor model gives a 2.4% monthly return, and the annualized Sharpe ratio is almost 2. This is these numbers outperform the 5 factors. You see the Q factors and the RPPC factors. Okay, and our results are persistently strong for outer sample. But outer sample period, we have 1% alpha against the market, and for the mean variance efficient version, we have 2% alpha against the market factor. We got a question. These annualized numbers. Okay, thanks for this clarified question. The average return is monthly average return. Okay, the alpha is also monthly. The Sharpe ratio is analyzed the Sharpe ratio. All right. So the final takeaway is that we develop a panel tree factor model that is adapted to the panel data structure in finance. We can generate basis portfolios. We can generate a factor that is strong in both asset pricing and also investment. Panel tree offers an alternative way to sort the cross-section. This is a top-down solution to security sorting. We can split the cross-section of stocks into some basis portfolios based on their characteristics. And in this paper, panel tree is guided by the long arbitrage criterion, and our loss function is to minimize the pricing error. In applications, you can adapt this to other purposes. For example, if your purpose is simply for portfolio management, you can change the split criterion to the Sharpe ratio of your portfolio, or to the average return of your portfolio, to the information ratio of your portfolio, anything you like. So you can adapt it to by your purpose. Okay, So for the empirical finding, we use the equity stock, US equity data. We find our factors are very strong, and the investment performance is also very strong. So this is one way we use the panel tree framework to generate the factors. We can use panel tree for other economic research and other applications to finance. So I think I have to conclude here. Thanks for your attention, and I look forward to your questions.